One of the things that is a common misunderstanding about switching from Python to Rust is that, hey, it already works with Python. I don't want to rock the boat. Let's go ahead and stay with the language that I'm productive in. Well, I'm going to show you a use case here where I do think many intelligent people should consider the energy efficiency of the Python language. And in particular, I'm going to talk about two different things. First, a study that shows the energy and time comparison across languages, and we're going to use C and Rust really as the same thing. They're basically, in terms of energy efficiency, computational power, effectively equivalent. And we're also going to talk about Python in terms of where it ranks in terms of energy efficiency and also computational performance. And I'm going to talk about two different studies. And I think what you're going to find out is that there isn't a really good reason in many scenarios to use Python for heavy computational loads, especially static loads, where you're deserializing JSON back and forth like a web microservice. And you should consider the carbon footprint of the code you're writing, right? We know definitively there is a problem happening on Earth. We need to think about how we use our resources. And if you can easily switch from one language to the other, especially with a tool like Copilot, you should at least consider it. And that's really the goal of this, is to help you think about the problem of energy efficiency by the language you personally are using, and to at least make an informed decision about what you want to do going forward. All right, let's go ahead and get started. Here we have a very fascinating paper about ranking programming languages by energy efficiency. And you can see here that there's a lot of research into this area, and it's about comparing programming languages regarding the efficiency from an energetic point of view. And if we go ahead and get right down to the crux of it, you can see that the two most energy efficient languages, if we normalize for global results and different operations, is going to be C and Rust. So effectively, they're equivalent, right? You can see that for all intents and purposes, if you say C, you say Rust, they're about the same. And then in terms of computational time as well, you can see the difference between C and Rust are effectively the same. Now, how does this compare to Python in particular, the most popular language on Earth? Well, we can see that, in fact, for all intents and purposes, Ruby, Python, Perl are pretty close in terms of the energy they use, and also pretty close in terms of the time they use. So basically, it's 70 times more energy is being used by Python in equivalent interpreted languages. Also, in terms of computational time, you can see here that it's about 70 times longer to do something in Python. In terms of memory, there also are some issues in terms of Python here. You can see that if you compare it to Rust, it's about double the memory usage. And we're not even talking about multi-threaded programming, which is something that Python is not able to do across multiple cores due to the global interpreter lock. And so people use multiprocessing instead, which is a memory-intensive operation. So in a nutshell, if you do care about energy, you do care about computational time, Python is one of the worst performing languages for both. And from a sustainability perspective, this is something your organization should consider. If it's easy to switch to Rust, would you do it? And I think that's really one of the questions that organizations should ask. Now, let's dive into another one that talks about this idea of computational performance. Recently, I was at a talk from Dr. David Patterson at Google, and he brought up this exact slide that talks about matrix multiply speed up over native Python. And I was actually able to ask him a question about this slide. And what he's mentioning here is that matrix multiplication, so depending on how you craft your code and what it is you're specifically doing, could be 62,000 times faster over native Python code. So really what we're seeing here is that Python, in terms of computational performance, really isn't a great language to use. And it's something that people should consider. Like, what are the alternatives? And can I do it? Can my organization do it? Can I use tools like Copilot, for example, to help me level up to a language like Rust? And if we look at the syntax, we can really see that Rust isn't too different than Python, and the gain you're going to get by uh, really deeply considering speed up and deeply considering energy efficiency. Not only could it make an impact in terms of your budget, right? You could maybe save 50, 70 times computational cost for a cloud provider, but you also could be being thoughtful about the sustainability goals of your organization. One of the more powerful ways to use Rust is to build a systems tool that talks to a GPU. Fortunately, because PyTorch bindings work so well with Rust, what I'm going to do is piece together a tool that can not only talk to the CPU and saturate it via PyTorch, but also can talk to a CUDA-enabled GPU saturated with PyTorch, and then use some of the advantages of Rust, which is the true cores that allows you to spawn a pool of threads and then send data into a GPU to try to get the most out of it in terms of a stress test. Let's go ahead and build that tool in just a few seconds. Let's take a look at the architecture of how you could build a stress test tool for a CUDA-enabled GPU by using the systems programming capabilities of Rust and the helpful Rust PyTorch bindings. First up, we have to have access to a CUDA-enabled GPU with GitHub code spaces. That's one way to do it. It could also be a AWS instance or a GCP instance or an Azure instance. We then configure NVIDIA SMI monitoring. So next up, we look at how the GPU is being able to be utilized during our stress testing. Then we hook together the Rust PyTorch bindings. Once those Rust PyTorch bindings are enabled, then I build together a Rust command line tool. And I have three different ways that I execute my stress test. I have a CPU, a GPU, and then I use the true thread and the powerful multi-threaded but memory efficient capabilities of Rayon. And I shove data into a GPU in a multi-threaded fashion to do a full stress test. All right, let's go and get started. Okay, let's go ahead and get open this environment here. I'm going to go ahead and launch it. And we can actually very easily get started with building out this stress test. And some of the things to take care of right out of the way is to make sure that we've got the correct cargo structure set up. That's really one of the key takeaways here. And it's probably easy to go through and first run this to see how it works, and then we can see what are the changes we want to make in the future. So here I have a translate app. That's one, and I also have a stress app. I'm going to go ahead and use the stress one, and this one is pretty interesting because if we look at the cargo file, we're using three dependencies. First up, we have the Chameleon tool. Second, we have the PyTorch bindings for Rust, and then we have Rayon, which allows us to do multi-threaded code. That's all I have to do to build this stress test tool. Next step, I again use this pattern. My library code lives in lib.rs, and my Chameleon tool lives in main. Let's go ahead and take a look at the library code first. Here, inside of the library code, we have functions that are built, and each function is quite simple. So I have the Rayon imports, I have the TensorFlow imports, but if we look at this, you can see that I build a load test, and all it's doing is sending a vector into the device. In this case, it's a CPU, and it's going to print out what's happening. In this case, I build a GPU load test function. So we just change the device. So we say, look, I want to actually iterate into this CUDA device. And then finally, all I need to do to change is to have a multi-threaded version of this is just use this into par iter for each op, and then throw that into the CUDA device as well. So what's really cool about this is we have three completely different ways to actually utilize testing. Now, all I need to do is go over to my main. And again, it's the exact same pattern. This is essentially boilerplate code. Here's the stuff that matters. I build out a CPU subcommand, I build out a GPU subcommand, and then I build out a T GPU subcommand for multi-threaded. And look, I just map each one of those to the library code. So this pattern is so powerful because you build just a few lines of code in a library, and then you map those functions into here. The only other thing you have to do to be aware of is make sure that these are each pub. Once you've done that, you're good to go. Now, all I need to do to run this is go ahead and run cargo. So let's go ahead and build that. We'll say cargo and then say dash dash help. And we can say cargo run help. And this will go through and compile it again. And it'll give us a help menu, which will correspond directly to each of these commands, the CPU, the GPU, and the Chi GPU. And that's exactly what we see. Now, one of the things that's really helpful is to do two kinds of monitoring. First up, let's go ahead and do each top. And let's go ahead and take a look at the CPU here. So if we go through here and we look at the CPU, and I run cargo run, and I say CPU, what's going to happen is it's going to throw a bunch of data into the CPUs, and look, you can see it's saturated, right? Now, if I go over to the GPU monitoring, you'll see nothing's happening, right? So this is a great way to understand what's going on with your code, right? We know that we're using the CPU device, so no traffic is going to the GPU. So next, what I'm going to do is now we're going to change gears here. You can see I've stopped. And I'm going to go through and I'm going to say, okay, let's go to the GPU. Now, what happens when you go to the GPU? We'll do a GPU stress test, and lo and behold, it's going to send a bunch of data into the GPU. We'll be able to see it by toggling right here, and you'll see this thing getting saturated. Now, it only really gets up to, let's say, a quarter of the load. And if we look at the threads here as well, they're still being utilized. So basically, the cores are still being utilized, but some traffic as well is being sent to the GPU. Now, can we do better than this? Can we get this load higher if we really want to stress test things? Well, we can, and that's where the threaded GPU comes into play. And that was the code I wrote earlier that uses Rayon. And now let's take a look at this. There we go. So we've been able to actually more than double the load that's getting sent to the GPU, right? It was really around like 20, 25%. So let's say it's been 2 to 3 times more load. And now if we look at the CPU, check this out. Notice how it's actually reduced the load of the CPU. So you can see here, once you start putting enough traffic into a GPU, it's actually a great way to offload some of the resources on your system. So what's really great about doing stress testing for a tool like this is to really get a feel for what's happening in your environment. Unless you do a benchmark, you really don't know what's happening, especially in the distributed computing problem, like doing PyTorch training on a GPU. And you can see here, Rust is the perfect tool to do training, to do inference, to build portable binary tools. And really, Rust is the systems tool that is an ideal tool for MLOps.